Hello everybody, myself Jyoti and this is the sixth lecture of Spectra of Diatomic Molecules. So if you have seen the previous lectures, earlier we considered diatomic molecule as a treated as a rigid rotator. ठीक है, हम we found out the rotational energy of a diatomic molecule by treating it as a rigid rotator. But उसमें हम लोगों को मिला था कि the spectral lines are equidistant, but later on we found that the spectral lines are not equidistant, so we cannot treat diatomic molecule as a rigid rotator. Then we treated the diatomic molecule as a non-rigid rotator. After that, again we encountered some problems, so we treated it as a simple harmonic oscillator. But now we are wrong. We cannot consider diatomic molecule as a simple harmonic oscillator even. Why? Because experimental observations show that vibrational spectra consist of a very prominent line at nu zero, but in addition, a few weak lines with decreasing frequency and spacing are also observed. When we are treating diatomic molecule as a simple harmonic oscillator, हम लोगों को क्या? We get just single line of a single frequency. That was what was the conclusion if you have seen the previous lecture. But here in practice, what do we get? We get a very prominent line at nu zero, but along with that हम लोगों को additional lines मिलता है with weak lines, you can say, of with decreasing frequency and spacing are also observed. So इसलिए हम लोगों को अभी diatomic molecule will have to treat it as an anharmonic oscillator. So diatomic molecule as an anharmonic oscillator, this is the more realistic model. So for a simple harmonic oscillator, potential energy curve is a parabola. ये आप लोगों ने पहले भी FY में पढ़ा होगा, फर्स्ट ईयर सेकेंड ईयर में. So simple harmonic oscillator में you have a potential energy curve which is represented by this parabola. Now what happens as the amplitude increases, potential energy also increases. In case of diatomic molecule, as vibrational quantum number nu increases, amplitude and potential energy increases. What is happening in case of a diatomic molecule? As vibrational quantum number increases, amplitude and potential energy also increases. But बहुत वाइब्रेशन हो रहा है. सपोज देयर इज अ डायटोमिक मॉलिक्यूल, एटम्स आर वाइब्रेटिंग विथ larger amplitude. There will be a point at which this bond between the atoms, it will break. So as the vibrational quantum number nu increases, amplitude goes on increasing, and there is a point at which the string breaks. String breaks in the sense जो bond है atoms का in a molecule, that bond breaks. And then we say that molecule is dissociated. When the atoms, they get separated from each other, तब हम लोग बोलते हैं कि molecule dissociate हो गया. Hence, a simple parabolic potential energy curve will not work for our diatomic molecule because it will not be able to explain dissociation of molecule. Simple harmonic oscillator में जो potential energy curve है, it cannot explain dissociation of molecule. इसलिए हम लोग वो diatomic molecule, we cannot treat it as a simple harmonic oscillator. We have to treat it as a anharmonic oscillator. इसलिए जो parabolic curve है हम लोग को वो भी नहीं चाहिए. We will want a more realistic curve when we will treat it as an anharmonic oscillator. Now anharmonic oscillator का जो कर्व है, इट कैन बी एक्सप्रेस्ड बाय डिफरेंट इक्वेशंस. बहुत सारे इक्वेशंस है. देयर इज नॉट अ स्पेसिफिक इक्वेशन, देयर आर नंबर ऑफ इक्वेशंस यूजिंग विच यू कैन एक्सप्रेस द एनहार्मोनिक ऑसिलेटर डिपेंडिंग अपॉन नेचर ऑफ द कर्व इट रिप्रेजेंट्स. बट हम लोग जनरली विच वी यूज इज मॉर्स कर्व. So for our diatomic molecule, we will use equation given by Morse, and that equation is this: V of R is equals to D into 1 minus e raised to minus a into r minus r0 square, where D, it is called as dissociation energy, r0 is the equilibrium distance between two atoms, and a is the measure of the width of the potential well. So we are not going into the details of deriving this equation. We are not bothered about that. हम लोग को anharmonic oscillator का कोई derivation नहीं करना है because there are number of equations. उसमें से हम लोगों ने एक पिकअप किया, mods, the equation which is given by Morse, we have picked up that, and we are just looking at what kind of solution we get rather than how we derive it. Okay, so we will just take this equation as it is and see this graph carefully. Here this is called as Morse potential curve, and you can, जो green में है parabolic और जहाँ पे मैंने harmonic लिखा है, this one, that is the actual potential curve, that is the simple harmonic curve. When we treat diatomic molecule as a simple harmonic oscillator, then we get this green curve which is represented over here. But when we talk about Morse potential curve, which is more realistic curve, it is the one which is given by Morse. See this one. Okay, now ye nu equals to 0, nu equals to 1, nu equals to 2, these are the vibrational quantum number. Ye jo hai na, these are the vibrational quantum numbers. Now if you see at less lower value of vibrational quantum number, like nu equals to 0, nu equals to 1, if you will check this part carefully, you will find that for lower value of vibrational quantum number, simple harmonic oscillator ka curve or Morse curve, both are close to each other or same. That means anharmonic diatomic molecule, it will behave as a simple harmonic oscillator when the vibrational quantum number has a lower value, nu equals to 0, nu equals to 1, and so on. But as the vibrational quantum number increases, if you go from nu equals to 0 to nu equals to 6, you will find that the parabolic curve, actually it is become wider. यहाँ पे you see this curve, it is becoming, ये जो है portion, this has become wider. ये this green curve is, sorry, this green curve is like this, but Morse curve is becoming wider when the vibrational quantum number goes on increasing. So these are the observations from the curve, that near the minimum the potential energy curve is parabolic, and hence for lower nu the molecule behaves as a simple harmonic oscillator. As vibrational quantum number increases, the potential energy curve becomes wider as compared to parabola. Now when I am saying that potential energy curve becomes wider, then there is one important interpretation of quantum theory. According to quantum theory of a particle in a box, energy level, wider the box, closer the energy levels are. ये बहुत important है, this you have to keep in mind. According to quantum theory of particle in a box, wider the box, closer are the energy levels. Hence the energy levels become closer and closer as nu increases. And finally, a state of continuum is reached as when the molecule dissociates. सो मैथमेटिकली अगर हम लोग v की वैल्यू कैलकुलेट करें जो मॉर्स कर्व से आई है, इफ वी सब्स्टिट्यूट दैट वैल्यू ऑफ v इन स्क्रोडिंजर्स इक्वेशन एंड वी कैलकुलेट द वैल्यू ऑफ एनर्जी, वी गेट दिस एक्सप्रेशन E nu, it is equals to nu plus half h nu 0 minus nu plus half h square nu 0 square upon 4d. If you look at this first term is same as the value of energy which we got for simple harmonic oscillator. Simple harmonic oscillator को के जैसे ट्रीट किया था डायटोमिक मॉलिक्यूल को, तो हम लोग को वैल्यू क्या मिली थी एनर्जी की, E nu is equals to nu plus half h nu 0. बट यहाँ पे when we are considering it as an anharmonic oscillator, there is one term which is additional. ये जो term है second term, that we are getting, that is the additional term when we treat the diatomic molecule as an anharmonic oscillator. So the second term, it produces anharmonicity, and because of this term vibrational levels are not equispaced. When we treat diatomic molecule as a simple harmonic oscillator, what do we get? We get that vibrational energy states are equispaced. Half h nu 0, then 3 by 2 h nu 0, then 5 by 2 h nu 0. Spacing between two energy levels, it is of the order of h nu 0. याद है लास्ट लेक्चर में हम लोगों ने किया था. बट यहाँ पे क्या होता है, ideally we got the result that the vibrational energy levels are not equidistant. So why it is not equidistant? Because of the second term. This produces anharmonicity, and because of this vibrational levels are not equispaced, the spacing decreases. Wider the curve, the spacing between the energy levels will decrease. So as nu, that is vibrational quantum number, increases, the spacing decreases. So vibrational spectrum, When a diatomic molecule is considered as an anharmonic oscillator, selection rule is delta nu equals to plus minus 1, plus minus 2, plus minus 3, and so on. If you remember, when we treated diatomic molecule as a simple harmonic oscillator, the selection rule was delta nu equals to plus minus 1. What does it mean? That transition can take place between two successive energy levels. सपोज 0 है और 1 है, उसके बीच में ट्रांजिशन होगा. एनर्जी लेवल 1 है और सेकेंड है, उसके बीच में ट्रांजिशन होगा. 0th लेवल और सेकेंड लेवल में ट्रांजिशन नहीं होगा. That was the selection rule in case of simple harmonic oscillator. When we talk about anharmonic oscillator, diatomic molecule treated as an anharmonic oscillator, selection rule is plus minus 1, plus minus 2, plus minus 3, and so on. That means any transition is possible. 0th लेवल से फर्स्ट लेवल पे भी हो सकता है, 0th लेवल से सेकेंड पे भी हो सकता है, 0th लेवल से थर्ड लेवल. डेल्टा n इक्वल्स टू प्लस माइनस 3 क्या है? थर्ड और 0th लेवल के बीच का ट्रांजिशन. दैट वे. सो दो ट्रांजिशंस लाइक what was the problem when we treated diatomic molecule as a simple harmonic oscillator? We said that only one prominent line is observed, but practically हम लोगों को क्या मिल रहा था? Along with one prominent line at nu zero, along with that few additional lines with few weak additional lines we used to get. अभी यहाँ पे हम लोग को रीजन पता चलेगा. So though the transitions for delta nu plus minus 2 plus minus 3 are allowed in case of anharmonic oscillator, they have very small probability occurrence. Probability बहुत कम होता है. Probability decreases with increase in delta nu, and means probability for delta nu equals to plus minus 2 ज़्यादा है, delta nu plus minus 3 कम है, delta nu plus minus 4 और कम है. That way. So also since at room temperature most of the molecules are at nu equals to 0 state. ये इसका मतलब क्या है? If you remember, I told you that the energy change in case of vibrational energy state, it is of the order of 0.1 electron volt. At room temperature, what is the energy which is available for the molecule? It is given by the thermal energy, E equals to 3/2 kT. 3/2 K यानी बोल्ट्जमैन कांस्टेंट, T यानी रूम टेम्परेचर. अगर तुम लोग ये वैल्यू सब्स्टिट्यूट करते हो, सो थर्मल एनर्जी विच इज अवेलेबल एट रूम टेम्परेचर, उसका वैल्यू तुम लोगों को मिलेगा 0.025 इलेक्ट्रॉन वोल्ट. सो दैट मच एनर्जी इज अवेलेबल. अवेलेबल थर्मल एनर्जी कितना है एट रूम टेम्परेचर? 0.025 इलेक्ट्रॉन वोल्ट. वाइब्रेशनल ट्रांजिशन होने के लिए हाउ मच एनर्जी इज रिक्वायर्ड? 0.1 इलेक्ट्रॉन वोल्ट. That means at room temperature that much energy is not available. So that is how most of the molecules, they are in the ground vibrational state. Okay, this is very important. You remember that most of the molecules at room temperature, they are in the ground vibrational state, and therefore most of the molecules, they are at the nu equals to 0 state. That means ground state, and only the transition from nu equals to 0 to nu equals to 1 is conspicuous in absorption spectrum. Other transitions from nu equals to 0 to nu equals to 2 or 3 do occur, but are very infrequent, very weak in intensity. Probability is very, very less. Vibrational spectrum, it lies in infrared region. Now the question is, why homonuclear diatomic molecules do not exhibit vibrational spectra? Similar question we have already studied in earlier lecture, and the answer is just the same. Question था last lecture में, why homonuclear diatomic molecules do not exhibit rotational spectra? Same reason है vibrational spectra के लिए. Now homonuclear diatomic molecules have permanent dipole moment, जैसे कि H2, O2, N2, दोनों atoms same. That means it is homonuclear molecule. So homonuclear molecule में क्या होता है? They have permanent dipole moment, and vibrations do not produce any change in the state of dipole moment. According to classical electrodynamics, vibration of only those molecules can lead to absorption or emission of radiation which have a changing dipole moment with their motion. Vibrational spectra के लिए या फिर rotational spectra के लिए you need changing dipole moment. Changing dipole moment you can observe in case of heteronuclear diatomic molecules, जैसे कि HN, HCl, CO, दोनों atoms different है, C और O. both atoms are different. So in case of heteronuclear diatomic molecules, you can observe, you have a changing dipole moment, and that is how you will get vibration spectra, rotational spectra. लेकिन अगर होमोन्यूक्लियर है, H2, O2, N2 ऐसा कुछ है, तो you cannot get, it does not exhibit rotational spectra, it does not exhibit vibrational spectra. Very important point. Now, pure molecular vibrational spectra are observed only in solids and liquids. क्योंकि solids and liquids में vibrational motion it is dominant as compared to rotational motion. So when you talk about solids या liquids, उसमें mostly क्या होता है, molecule they exhibit vibrational motion, atoms are continuously vibrating, लेकिन rotation of molecule as a whole it is not dominant, वो नहीं होता इतना. So that is how you get pure molecular vibrational spectra. But in case of vapor, अगर आप vapor का example लेते हो, तो then we observe that in vapor along with the vibration of atoms there is a rotation of molecule also. सो इन दैट केस जो स्पेक्ट्रा हम लोगों को मिलेगा दैट विल बी मिक्स्ड स्पेक्ट्रा, उसमें हम लोग को वाइब्रेशनल स्पेक्ट्रा भी मिलेगा, रोटेशनल स्पेक्ट्रा भी मिलेगा. सो इन दैट केस दैट द वॉट एवर स्पेक्ट्रम वी गेट इट इज कॉल्ड एज वाइब्रेशन रोटेशन स्पेक्ट्रम. ओके, थैंक यू.